We are in Dolní Břežany, near Prague in the Czech Republic, where the ELI Research Center is located. This institute has the extreme high-energy laser applications as its main field of interest and activities. In this site, 3 of the most powerful laser generators in the world are installed. Under a contract of ELI, the Fantini SPA company has designed, manufactured, and installed 6 very large experimental vacuum chambers, able to operate at a vacuum pressure of 10 to the -6 millibar.
This chamber will be the environment in which laser-matter interaction will be investigated for different experimental beamlines. One of these experiments, named the Rimaya Helimed, will have the main task to develop laser-based technologies and processes for an innovative branch of hadron therapies against cancer.
The Fantini SPA company has a deep interest in developing a strong cooperation with the ELI Institute and other research centers and institutions working on new and advanced technologies based on its long experience with vacuum vessels, structures, mechanisms, system-level design and management, and integrated design and manufacturing processes.
Our tasks consist in the supervision of many Italian and international research projects, supplying with structure and scientific apparatus and equipment. Our team is joining theirs in a truly advanced research in physical and biomedical fields. Internationally supported, the goal is to drive laser research to new frontiers up to increase technology's potential, meeting the needs of our community. Our part in this project was to build in our Italian factory the vacuum chambers necessary for the laser-based experiments.
My name is Daniele Margarone. I'm a senior researcher at ELI Beamlines. This is an international project where we are going to use the most powerful laser in the world for basic science, but also for multidisciplinary applications, so application in society. Here you can see the Rimaya beamline. This is an ion accelerator, very compact, driven by lasers. So what we do is we try to accelerate in a very short distance, less than a millimeter, ions to very high energies, up to few hundred MeV. And then our user will try to investigate different applications. One important application we are envisioning is in the medical field, so-called cancer therapy, hadron therapy. And you can see different sections of the beamline. Here there is a vacuum chamber produced by Fantini in Anagni, Italy. And this is used for the acceleration of ions in vacuum. So the laser is focused at ultra-high intensity, and the laser-matter interaction generates ions, protons that are accelerated downstream the beamline. The second part of the beamline is called ELIMED, ELI Medical Application. It was developed by INFN.
We want to provide to the user a beam which is suitable for irradiation, so it's well characterized, well selected in energy. And the concept behind these magnets is to select a beam starting from our source, which is a polychromatic source.
ELI Beamlines is already improving research on oncology treatments and biomedical imaging, and also searching for new methods of nuclear waste processing. The experiments in vacuum chambers will have applications in many different areas, like astrophysics, chemistry, and medicine.
Our goal is to create a 10 GeV electron accelerator using laser as a pumping media. So we use a plasma accelerating cavity to reach these high energies. And the reason is that if you use conventional particle accelerators, like for example the CERN, which is very famous, or SLAC in the US, or Fermilab, you can see they're very big in size. They're like tens of kilometers. So now we're trying to do the same kind of particles with the same energy or similar energy in what you see here is about 10 meters.
Why we need such a big vacuum chamber with a good level of vacuum is because of the size of the beam and the fact that to make it really high intensity when it's focused, we will use a different parabola that are basically huge mirrors, but these are curved mirrors. So they take the beam and they will focus down, but the focal length can vary, can be from a few meters up to very long distance, like 20, 30 meters. One of the main research and the work that we are doing here is to optimize the laser interaction with the target in a way to tune the parameters of the electrons like we want. So to produce high energy electrons or to produce a very collimated beam if this will be needed to do some radiotherapy. So like in medicine, the beam should be very collimated and we should give to the external user or to the doctors in future a very precise and tunable control on the laser and electrons.
What people do nowadays in kilometer scale, we will do in few meter scale. So really, we can use this completely new radiation source. We can use it in many different fields because basically we're going to reduce the size and the cost of such technology. So we are very optimistic and we hope that we will help the society in the short term.
Since the beginning, it has been a great team effort where everybody is still giving his best dealing with a complex technology. We are talking about new research fields, experimental technologies not yet widespread. Dealing with these challenges, the Fantini Group are proud about working in such a long-term, wide-ranging project that has a great value in the academic and industrial world, but also has many expected social benefits.